Welcome to the School of Chemistry here at the University of Bristol. Welcome to Bristol ChemLabs. My name is Tim Harrison. I'm one of the academic members of staff in this department. This lecture demonstration is entitled Gases in the Air, and during the demonstration we're going to hopefully show you some of the fascinating chemistry of the gases that you are sucking in and out of your lungs. Now, most of you will be aware that the main two gases in the air are nitrogen and oxygen. At 78%, nitrogen is the biggest gas in the air on planet Earth, followed by 21% oxygen. The two main gases take up 99% of the air that you're breathing in. All the other gases you can name are in the last 1%. Most of that last 1%, 0.93%, is a gas called argon. In fourth place on planet Earth, the biggest gas in the air, the fourth biggest gas in the air, is carbon dioxide. And that's currently running at 407.8 parts per million as of the start of 2020. Carbon dioxide levels are increasing. Every other gas you can name is in the atmosphere in what we call trace gas quantities, tiny amounts, including the gas that's filling these balloons that are behind me. Most of you looking at these balloons will think that these balloons are filled with the low-density gas helium. In fact, you'd be partially correct. We have helium in this balloon here. I know it's helium because I remember putting a knot in the string. In this balloon to my left is the other low-density gas that makes balloons float, and that's a gas called hydrogen. Now, whilst hydrogen makes up 99.99% of the visible universe and helium follows in second place, in the atmosphere, in the air that you're breathing in, each are only present at 1 part per billion. A billion is 1,000 million. So it's a tiny, tiny amount of the air you breathe. These two gases are completely different in chemistry and in physical properties. Whilst both are lighter than air, helium is actually lighter than hydrogen in equal volumes. Helium gas, however, is used in party balloons, and that's because it's a relatively safe gas. It's not poisonous and it's not explosive. In a moment I'm going to try and set fire to the helium that's inside that balloon. Hydrogen, on the other hand, not a particularly safe gas. The hydrogen I've got in here, just like hydrogen anywhere else, is potentially explosive. Let's set fire to both so you can see that there is a difference. So we'll just light up these wooden spills from my Bunsen. This is the helium one, the party balloon gas. It simply bursts as though an air-filled balloon would be bursting. Let's try hydrogen. Look to see the difference. So apart from the noise, which you can't see, you can see the flames that came out as the hydrogen gas did its chemistry with the oxygen in the air. And in burning hydrogen gas, as we did very quickly, quick burning is called an explosion, we're producing hydrogen oxide, and hydrogen oxide is simply called water. Burning hydrogen gas makes water. Let's get rid of the Bunsen burner for now. Let's concentrate on the biggest gas in the air. Rather than these trace gases, let's look at nitrogen gas. Nitrogen is 4 out of every 5 breaths you're breathing in on average. 78% to be precise. Nitrogen has no colour, it's a colourless gas. It has no smell, it's an odourless gas. And it has no taste. There's already nitrogen gas, there's air inside your mouth. It has no taste. It's odourless, colourless and tasteless. It's pretty boring. If we try to explode it, nothing happens. If nitrogen gas was replaced by hydrogen, the first spark, the first lightning strike, would explode the entire atmosphere of planet Earth, using up all the oxygen, and if that had happened, none of us would have ever been born. Nitrogen gas is boring. That's not to say it's useless. We can use nitrogen to make this stuff. This is expanded polystyrene. It's not simply polystyrene, it's expanded polystyrene. Polystyrene is a polymer, a plastic, and we use gases to turn it into polystyrene foam. Most of what you're looking at here in this piece is gas, and I can show you that. The gas they tend to use these days is nitrogen. I'm going to add a bit of the active ingredient nail varnish remover into this beaker. It's a chemical called acetone, or more correctly in school level chemistry it's called propanone. Large beaker, small amount of propanone, big piece of polystyrene foam. Just watch what happens. If you look at the interface here, if you can see, that's where the gas is being released. Now you might be thinking, oh, the polystyrene foam is melting. That can't possibly be true because I'm not heating it. You might think I've dissolved the polystyrene foam. If I did, I'd make a solution. And you can see there's simply a blob of polystyrene in the bottom of that beaker. All I've done is disrupted the structure. If you want to know how much polystyrene is in polystyrene foam, we can do a measured experiment. We can do a quantitative experiment. Here I have a litre of polystyrene packing pieces. They just happen to be coloured green. Let's see how much polystyrene is actually in a litre of polystyrene foam. I'll use the same liquid as before. I'll put the lid on because it smells. There's not a lot of polystyrene in polystyrene foam. I do notice that floating about in a bottle of this sample is a piece that I thought was polystyrene foam that isn't. There is a substitute for polystyrene foam that's made out of corn, it's made out of maize, and that will not dissolve in acetone, in propanone. But if I replace the solvent in there with some hot water, it would collapse. I suppose that's one way of separating out polystyrene from the maize equivalents. Let's get rid of that. As I said, it's not nice. Nitrogen as a gas, pretty boring. It's fairly unreactive. If nitrogen gas were reactive, in the presence of oxygen in the air, it would make nitrogen dioxide. We'll have a quick experiment to show you some nitrogen dioxide. I have here some pieces of copper that I'll just put into this container. I need to track down one other chemical. I need to track down some nitric acid, which was under my nose all the time. Nitrogen dioxide, if it were formed when nitrogen and oxygen gas in the air were to react, which it will do during a lightning strike, but not normally, we'd be able to tell that we changed the chemical because of the colour. Nitrogen dioxide is a coloured gas. It's that browny orange colour that you're seeing being produced in the container. Now that gas is also quite poisonous. I'm not making enough to damage me, but I do want to stop the reaction. So I'm just going to add a drop of water in there to slow and stop the reaction. If you were in my lecture theatre smelling this gas, you'd smell a little bit like chlorine. But we know it's not chlorine because chlorine is a yellow-green poisonous gas, and this is a browny-orange poisonous gas. Let's get rid of that. Now, if you take any gas, nitrogen gas for example, and you cool it down, you should be able to cool it until it condenses into a liquid. Liquid nitrogen is possible. If you get some nitrogen gas and cool it down to a temperature of only minus 196 degrees centigrade, it will form liquid nitrogen. For those of you that don't know, minus 196 degrees centigrade is roughly 220 degrees colder than the air in this lecture theatre. And to put that into context, Your fridges are quite cold. They're about 20 degrees colder than the air here. Your freezers are even colder. They're roughly 40 to 45 degrees colder than the air in a room. And if you were stupid enough to go down to the South Pole midnight, midwinter, it's about 60 to 65 degrees below zero, or 80 to 85 degrees colder than the air in this lecture theatre. And that's the coldest temperatures that you'll get on planet Earth. Liquid nitrogen's even colder, so it doesn't form naturally. I'm going to pour some liquid nitrogen into this specialised piece of glassware. This is called a Dewar flask, named after its inventor, a Scotsman by the name of James Dewar. It does allow me to put a very cold liquid into a container and to be able to handle it. My liquid nitrogen is in a bigger Dewar flask. This will keep my liquid nitrogen liquid for up to 5 days, and if I wanted to, it'd actually keep my coffee boiling hot for 5 days, because it doesn't let heat in or out. Look how thick the insulation is on the lid to stop heat passing through the lid. Right, liquid nitrogen, one of the 5 coldest liquids in the universe. Let's have a look at it. What you're seeing is liquid nitrogen in the act of boiling. The piece of glassware, this Dewar flask, was at room temperature. The glassware was 220 degrees centigrade hotter than the boiling point of the liquid. So liquid nitrogen is taking the heat energy from the inside piece of glass and is using it to boil. Boiling is a term we use to describe a liquid becoming a gas. Boiling does not describe the weather. I don't know what the temperature outside is for you guys today, but it's certainly not boiling hot as some people would describe the UK in an August weather situation. If everything was boiling outside, it would all be turning to gas. This is boiling, but it isn't hot. It's boiling at 220 degrees colder than air temperature. Now it's calmed down, we can discuss why there was some white stuff coming off the top. That white stuff isn't nitrogen. We would have noticed if 78% of the air was nitrogen and nitrogen was white. We'd be like living in a cloud. In fact, cloud is a good description of what's being produced here. Because as the cold nitrogen gas is coming out of the container, it's hitting the air. The air contains water vapour. When we breathe out water vapour. And when the cold nitrogen gas hits the water vapour, it cools it down and condenses it to billions upon billions of tiny droplets of liquid water. Those tiny droplets of liquid water are what we call cloud. Clouds are liquid. Watch. Isn't that gross? That was the water vapour that was inside my lungs, inside my body 1 second beforehand, coming out, cooling down and condensing, forming cloud. Right, now we've got the thing calmed down. It's no longer boiling like mad. It's because the inside piece of glass is at the same temperature. We can do some science. I've got here some pieces of rubber tubing. It's been in this lecture theatre for at least a few days, so I know that the temperature of this tubing is room temperature. Now, bizarrely, it does mean that the temperature of this tubing is 220 degrees centigrade hotter than that liquid, because liquid nitrogen is 220 degrees colder than the air. If I put the end in, this happens. I can make it rain nitrogen. And if I want to, I can have a quick shower in liquid nitrogen. That's not recommended. And it stops. And the reason it stops is because the heat energy that was in this bottom part of the tubing has been given to the liquid. It caused liquid nitrogen to boil. Some of the nitrogen gas then pushed out any unsuspecting droplets of liquid that got in the way. And when it stops, we know the bottom part of the tubing is the same temperature as the liquid. This is now dangerously cold, the bit that was in the liquid. It's so cold, if I was stupid to hold onto it with my hand for 5 seconds, my flesh would freeze to its surface, and when I pulled my hand away, bits of my dead flesh would be left on it. And I'm not going to do that even for a video. That's too dangerous. Cold temperature dangers have their own word. They call it a cryohazard. You notice if I hold it against my black lab coat that there's a white stuff appearing on the bottom of the tubing. Colour change usually signifies chemical change. Let me show you what I mean. I've got here 2 chemicals dissolved in water, so they are solutions. They're colourless solutions because they haven't got any colour. And we'll put one in there. To start with, I'm going to add a second one. Watch. That's a piece of chemistry going on, and it's signified because there is a colour change. Not all chemical reactions have a colour change. This one happens to be quite a pretty one. But that yellow will stay yellow from now until the end of time. It's an example of an irreversible chemical change. Have a look at this. Here are 2 bottles that have been on the bench all the time I've been talking. And they just look colourless. Let's give them a good shake. Shaking them up allows oxygen from the air in the top of the bottle to go into the mixture of chemicals in the solution to bring about a chemical change. And after a few minutes, maybe 5 minutes or so, it's a warm day today, those 2 solutions in the bottles will go back colourless again. That's an example of a reversible chemical change. Yellow stays yellow forever. Irreversible. White stuff on the end of the tubing, nothing to do with chemistry. It's warmed up while I've been talking, so it's now safe for me to do this. That white stuff is simply ice. You might want to call it frost, you might want to call it snow. It's not that I've turned the rubber into a new chemical. The ice has formed on the surface of the tubing. Let's figure out where that came from. Let's cool the tubing down again. In fact, let's cool me down again. I'm getting a bit warm. Water vapour in the air we can't see. H2O as a gas. It's hitting the tubing, cooling down, forming this cloud, which we now know is tiny droplets of liquid water. Some of those droplets of liquid water are now hitting the tubing, cooling down further and freezing into solid water. We've gone from water as a gas through water as a liquid by condensation, from liquid to solid freezing into solid water. It's still water, whether it's a solid, a liquid or a gas. Just happens to be the most common chemical that most of us ever get to use, and it has different names according to different states of matter. It's still H2O, whether it's a solid, a liquid or a gas. Changes of state are what we call a physical property change. Another physical property change is this one. Warm rubber tubing is squidgy. Okay, we call that being malleable if you want a technical name. The cold end, we can't bend. I've changed the physical properties. It's no longer bendy, it's become rigid. In terms of sound, that is a sound of warm rubber. That's the sound of cold rubber. Materials change their sound-making properties according to temperature. Let's get rid of that for a moment. Some of you might be curious why I've got some rubber gloves, some safety gloves on the bench, and I'm not wearing them to handle what is a potentially dangerous chemical. Well, I'm going to show you why. These are rubber gloves, proper rubber gloves, not the nitrile rubber gloves that you see with the blue ones. This is latex rubber. And I'm going to put one in the liquid to show you its properties when it's cold. Now please notice I'm not sticking my fingers in the liquid. If you stick your fingers in liquid nitrogen for 5 seconds, your flesh will freeze through to the bone. You can then snap your fingers off. I don't intend doing that for anyone. Right, it's been in there a few moments. Let's take it out. Why am I not using it as a glove? The answer is, when it's cold, it is far too brittle. It will not bend when your hands move. Let's warm it up a moment. I'm not waving it bye-bye, I'm just simply warming it up. It's a very thin piece of rubber, so it warms up quickly. And when it does, it's stretchy again. So that's an example of a reversible physical process, as opposed to my bottles here, which is a reversible chemical process. A few more experiments. Here we got a balloon. As a scientist, we love answering problems. We like answering questions. The question I've got here is a simple one. What would happen to the size of this balloon if I were to cool it in liquid nitrogen? Now, size cannot go bang. Balloons can go bang, size can't. Size will either get bigger, it will get smaller, or it will stay the same. And there's no point in guessing as to what's going to happen. Let's give it a go. There's the answer. Cooling down the balloon makes its size smaller. Let's warm it up in the nice warm air in this lecture theatre in Bristol. And it gets bigger again. This is a reversible physical property. But the interesting question is, why does it do that? Why does it do that? Interesting. Is it because the particles in the air inside the balloon, when they're cold, they shrink? Or is it because the particles inside the balloon, these atoms and molecules, when they get cold, so they simply huddle closer together? And the reverse, when it warms up, do the particles get bigger, or do they move simply further apart? Is it size? Is it distance? Well, let's see if we can work it out from this experiment. Here I've got two thick bits of glassware. Sidearm conical flask. There's a little spout here to which I've attached some balloons. Watch. You can see there must be a little spout there. I'm going to do two experiments at once. Scientists love doing repeats. I'm just repeating them at the same time. Let's pour in approximately 35 cubic centimetres, 35 millilitres of liquid nitrogen into this room temperature flask. And let's do something stupid. Let's seal a system that's producing a gas. Make a prediction, work out what you think is going to happen, and if it does happen, figure out why. This one's being a little more shy. Of course, not all balloons are identically thick. What's going on there? As the liquid nitrogen takes the heat energy away from the flask, it turns to a gas, it boils. The particles spread out. The particles, in becoming a gas, move further apart, fill up the balloon until the balloon can't take the pressure anymore, and the balloon explodes. And for those of you that like numbers, 35 cubic centimetres, 35 millilitres of nitrogen as a liquid will become 24,000 cubic centimetres of nitrogen as a gas. Same number of particles, they just spread out. Most of a gas is empty space, and that's why it's relatively easy to move through the air, a gas knocking the air particles behind you. You get up to your neck in water and try moving, and you'll find it's far more difficult. If you're trying to pull your way through the water, what you'll find is you can't do it as quickly because there are far more particles close together. You don't have the energy to push them around you as quickly. Let's leave nitrogen alone and let's move on to the second biggest gas in the air. Let's consider oxygen. We need oxygen to stay alive. We take oxygen into our lungs and we call that breathing. The oxygen then goes into our blood supply and actually does the chemistry that keeps us alive. It does what we refer to as respiration. Respiration is a chemical process where oxygen meets glucose from our diet, from the carbohydrates in our diet, in the cells in our body, in areas called mitochondria, and it releases energy for us to grow and repair and to allow us to move about and to keep our bodies at roughly 37 degrees centigrade. Respiration. Oxygen is also responsible for some chemical reactions as trivial as making those bottles change colour. Where we get our oxygen from is, of course, plants. I guess you guys, like most people, will have come across, depending on your age, the process of photosynthesis. Plants make oxygen. They don't set out to make oxygen. Plants take carbon dioxide and water vapour from their environment, and using the energy from the sun in the green parts of the leaves called chlorophyll, and they convert those chemicals, those simple chemicals, into sugars. The oxygen is the waste product. We live off a plant's waste product. Now, I can't make oxygen the way plants do. It's far too complicated, but I can make you some oxygen. We'll make it from this chemical. This chemical in here is a chemical a bit like water. Water is H2O. This chemical is water with an extra oxygen chemically attached. It's no longer H2O, it's H2O2, and we call that hydrogen peroxide. Hydrogen peroxide is an unstable chemical. It wants to fall apart, it wants to break up. And we can use the words dissociate or decompose for breaking up if we want to. Now, I'm going to use about 10 pounds worth of this chemical. It's about 200 cubic centimetres. I don't know from where you are, but whether you can see that it's actually forming any bubbles or not. I guess that's too hard to see for a colourless material and colourless glass. So let's add a bit of food colouring. Make it easier to see. Maybe you still can't see any bubbles or not. So let's add some washing up liquid to trap any bubbles that are present, any oxygen bubbles. And maybe we can make some foam. Let's give it a good mix. Now, whilst there are a few bubbles on the top of the solution there, I suggest that maybe I produced those when I was swirling it. This is a very slow piece of chemistry. If we wanted to just sit there and watch this till the rest of the day, another 7 or 8 hours, it might just fill the tube. And to be honest, I haven't got that amount of time to waste. So I'm going to do a chemistry trick here. I'm going to apply some chemistry knowledge, and I'm going to speed up the reaction using what I call a catalyst. Catalysts are simply chemicals that speed up reactions without getting used up. So we'll see if we can make some oxygen foam far more quickly. And there we have it. We're breaking up the hydrogen peroxide, the H2O2, back into oxygen and water. And it does it very rapidly. We have a huge amount of oxygen foam being produced. Now, I'm actually quite tempted to stick my fingers into that foam because it looks so good, but my brain tells me to do otherwise. I know that foam is over 100 degrees centigrade. That foam is hotter than boiling water, so sticking your fingers in is going to give you a heat burn. There's also some unreacted chemical in there, so that would give you a chemical burn. So that's a reason that I'm not going to touch it. But I am going to ask my friend and colleague here, Dr. Johnny Furs, to come in, because he's got safety gloves on. He's got a lab coat and safety glasses. Well, he nearly had his gloves on. And he's going to wrap it up and take it away, and then we'll get it cleaned up in the laboratories tomorrow when it's had a time to collapse. So that's making oxygen. What are we going to do with oxygen, apart from stay alive? Well, we need oxygen for reactions called combustion. In other words, burning. Without any oxygen, things don't tend to burn. So let's do a burning exercise. I've got here one of those fancy water bottles that you see in some offices and in some schools. And what I want to do is burn some of the fuel from drag racing cars. I've got here methanol. So drag racing cars don't use petrol or diesel, they use this biofuel. Now methanol is a bit nasty. Methanol is one of the chemicals that can pass through your skin into your blood supply, causing irreversible brain damage and death. So we don't want to touch it. What we do want to do is to shake this up like mad without it touching my skin. So I'm turning some of the liquid into vapour. If you don't like the word vapour, we could call it fumes. And I'm going to drain out the liquid. Scientists know liquids don't burn. It's not the liquid of a fuel that burns, it's the vapour of the fuel that is mixing with the oxygen in the air in order for combustion to take place. I've now got rid of most of the water, most of the liquid from there. I'm going to move that well out of the way. I've now got a fuel-air mixture. Fuel-air mixtures are explosive. So you've got to be careful with this. If you were in my audience here, I now put a safety screen in front to protect you for any potential mishap with flying bits of plastic. But you're not in the audience here, so I don't need to use one. Let's get a bit of flame sorted out. Let's add a bit of energy in. And we'll get the lights turned off in the lecture theatre because this will be easier to see in the dark, and there are 4 banks of lights to turn off, thank you Johnny. And we'll add a bit of activation energy in. And there we are getting the heat energy being released from the fuel-air mixture. I think we can have the lights back up. And just a few more to turn on. Okay, why the difference in the colour of the flame? Well, yellow flames are yellow because the fuel that's in it is camping gas, Bunsen burner. The fuel, when it burns incompletely, inefficiently, produces carbon. Sometimes we just call that carbon soot. Hot carbon atoms glow yellow. And that carbon could actually be further burnt to produce carbon dioxide and release more energy. So it's inefficient. The blue flame only produces carbon dioxide and water. All the energy in the fuel-air mixture gets converted into other forms of energy. Some light energy, we saw the flame, you might have heard it make a bit of noise, so we've got a bit of sound energy. And what used to be a water bottle is now a very hot water bottle, so we've got some heat energy, some thermal energy being produced. Chemically, as I said, we make carbon dioxide gas and water. You saw me empty this earlier. The liquid that's coming out is water. When you burn fuels, you make water. Let's clean up that mess. There are other ways of producing combustion without using oxygen gas. And we'll show you that here. Now, I've chosen as the fuel for this experiment, I've chosen the fuel that we all run off. We run off glucose, as I mentioned earlier. That's what that white powder is there, the C6H12O6 that's produced by plants. We've also got a second white powder here, an oxidizing agent. Now, oxidizing agents release oxygen. Fuels need oxygen to release energy. So if I actually mix the two together, a bit like producing cake, you're no good if you actually don't mix up your ingredients. The chemical won't be touching each other, so you may as well leave them in the bottle. They're not going to react. Okay, so on a special heat-proof mat here, so we're just checking, because I've got other mats here which aren't heat-proof. And to get the reaction going, I've got some concentrated acid, some concentrated sulfuric acid. And Johnny's insisting we're going to do this one in the dark, so that's all well and good. I can just about see. There is an alternative way of burning materials. And if you remember what I said just a few minutes ago, if you produce carbon, that's called incomplete combustion, and that's what we've got going on there. We saw a yellow flame, we saw a flame that produces a lot of smoke. Smoke is unburnt carbon, and we've got a lot of carbon left over. Smoke, by the way, is not a gas. Smoke is a whole pile of dust particles lifted into the air. Some of it could have been the sugar that was vaporized and then condensed back as a solid, and some of it would have been carbon that went into the air. And if you're worried about whether smoke is a gas or not, how do you tell the difference? Well, you fill a room full of smoke. What you then do is let it settle for a couple of hours, and everywhere, if it's a smoke, will have a thin layer of dust. A gas cannot settle. So we'll move that one out of the way. And that brings us on to the last but one set of experiments. And that's with carbon dioxide. Oh, it's really heavy. We're going to reload of our carbon dioxide, and I've got some in this box here. You might think that's pretty stupid, putting carbon dioxide gas in a box. And that's carbon dioxide in its solid state. Now, it may look like ice. It contains absolutely no water, so its nickname is dry ice. And what I'm flicking from one bit of skin to the other here is very, very cold. Dry ice is at least minus 78 degrees centigrade. If I kept the piece of dry ice on one part of my skin, I would get a cold temperature burn. In other words, frostbite. By moving it from one hand to the other, I can actually not suffer frostbite. If I was going to hold it for any length of time, or a bigger piece of dry ice, solid carbon dioxide, I'd have to wear gloves. Let's do just a couple of experiments with this. The first experiment I want needs a nice rubber glove. Here we have one left over. I'm going to put some dry ice into that glove. I'm going to, as you can see, it's the same rubber as in a balloon. Putting a knot in it simply makes a 5-digit balloon. I'm going to put my heat energy from my hand into the dry ice. I'm going to show you a rather weird property that dry ice has that most other chemicals don't. If you warm it up, it doesn't melt, but it does turn into a gas. It goes straight from a solid to a gas. And we call that change sublimation or subliming. Very, very unusual. I brought a frying pan over at the same time, and I'm just going to put this onto the dry ice. This is a normal frying pan. This one we got from Sainsbury's last year. Let's just put some on some dry ice and see what happens. Why does it do that? I'm not going to tell you. Ask your teachers. My favourite experiment with dry ice is definitely this next one. There is a big beaker. I'm going to add to it some tap water. Now this is tap water, not pure water. In using, and we'll do this against a white background, I think. We've got a second white background here. We can make use of this one. And I might take a third board to waft. If that is normal tap water, when I add this universal indicator or pH solution, it should go dark green, not the light green of pure water. Tap water contains dissolved minerals, which makes it very, very weakly alkaline. I don't want it to be green and weakly alkaline at the start of this experiment. I want it to be strongly alkaline. So I'm going to add some sodium hydroxide. turn it to pH 11 to 14 range, which is that beautiful purple coloration. Now we're ready to start. If you stand a chance of becoming a scientist, a technologist, an engineer or medic, you need to have great observational skills. I'm going to add this handful of dry ice into that solution. I'll then waft the clouds out of the way. And I want you to make observations, as many as you can. And at the end of the experiment, I'll go through my observations as a professional scientist. Okay, I'm going to stop wafting, it's tiring me out. We should get one more colour change before I finish speaking. Okay, so observations. Well, one observation I'm making, and it depends on how good your microphone is, I can hear a lot of bubbling going on. So that's one observation. I've noticed that dry ice sinks in water. That's a bit different from water ice. Water ice floats, otherwise icebergs wouldn't work. I can see bubbles of gas in the liquid. I can see a foam on top of the liquid. I can see some cloud being formed. I've noticed the cloud is white. I've even noticed that the cloud falls down the side of the container. Those are 7 observations before I actually look at the colour change here. It went from purple to blue. Blue became green. Green became yellow, and that yellow is now turning orange. Weakly orange, but it is turning orange. Those are 11 observations from just one experiment. Work out how many you got. If you didn't get at least half of those observations correct, practice your observation skills. They're important. Okay, now we're going to finish up, as we should finish all experiments with a bang. I've got 2 more balloons to show you. And to avoid disappointment, neither of these balloons is helium. Helium is far too precious to waste in doing these experiments when we've already seen it once. Helium we're running out of on planet Earth, and we need them for CAT scanners, for hospitals to see inside us. So both of these are hydrogen. I'm going to remind you in the light what setting fire to hydrogen looks and sounds like. And then I'm going to finish in the dark, so you can ponder this. The flame is the volume of reacting gases. Why is it that the volume of flame is bigger than the volume of the gas in the balloon? And after I've done this last experiment, that's it, I'm going for a lie down. So, the one in the light to start with. That's hydrogen doing its pop test. We'll now reposition the balloon. Get the lights off. Thank you for your patience. I hope you've learned something during this talk. Cheerio.